All right, so good evening, everybody, and I would like to welcome you all to our second seminar series under the Sustainability Seminar Series program that IIT Gandhinagar is having. So if you don't know, IIT Gandhinagar has a Kiran C. Patel Center for Sustainable Development, and that center does number of things, including research, capacity building, awareness, outreach, and part of the sort of mandate of the center is that we should invite accomplished researchers, practitioners who can enlighten us on the subject matter that is close to sustainability. So the first seminar we had last Monday, and that was on uh, water crisis or groundwater crisis by Dr. Deepankar Saha, and I'm sure many of you might have attended that as well. So today we have a very distinguished speaker, Professor Auroop Ganguly, and he is my mentor also, I can say, one of my mentors, so I am really excited to introduce Professor Ganguly for today's seminar. And many of you, I expect, that already know Professor Ganguly well. But if you don't know, I would introduce briefly that Professor Auroop Ganguly is a hydrologist and a civil engineer, and currently a professor of civil and environmental engineering at Northeastern University at Boston, United States. He is also director of Sustainability and Data Science Lab, that is called SDS Lab, and he is holding courtesy appointment in number of departments of Northeastern University, including computer science, marine and environmental science, political science, public policy, and urban affairs. He is visiting international professor of computer science and environmental science at Indian Institute of Technology, Kharagpur, and he is a member of United Nations Environmental Program Review Panel, and also the lead author of AI section of upcoming Sustained National Climate Assessment of the United States. Needless to say that Professor Ganguly has a number of high impact publications, and his research has been featured in Nature, Proceedings of National Academy of Sciences, Nature, Climate Change, and many other high impact journals. His research includes understanding of hydrometeorology, hydroclimate, extreme climate and weather events, resilience of lifeline infrastructure, data mining, and machine learning. Professor Ganguly has done PhD from MIT, and before his PhD, he did BTech from IIT Kharagpur. So with these words, if you want to know more about Professor Auroop Ganguly, please Google him. That is the best way. He has a Wikipedia page, if I'm not mistaken, and you can also go through his Google Scholar. Now, with this brief introduction, I welcome you all once again under this seminar series under Kiran C. Patel Center of Sustainable Development. And let's welcome everybody, Professor Auroop Ganguly, for today's talk. Thank you very much. And if you have questions, please hold until the end, or you feel free to write in the chat box, and we will have a question answer session of about 10 to 15 minutes at the end of his presentation. So, Professor Ganguly, you may please start whenever you feel.
Thank you very much, Vimal. It's a pleasure, as always, to interact with you and with IIT Gandhinagar. Can you hear me okay?
Yeah, perfect.
Okay, great. So today I'll talk about our work in climate adaptation and resilience engineering, especially with what can be broadly called machine intelligence for assessment of climate extremes. And I'll talk about what all that means. I'd like to thank Vimal, who I have had the pleasure of collaborating with for a while now. And also my former PhD student, Udit Bhatia, who is now a colleague of Vimal Mishra at IIT Gandhinagar. So I'm big fan of IIT Gandhinagar. I want all of you guys and the Institute to really succeed and go to the very top. So with that, let me start with the presentation. So I'll talk about some grand societal challenges in the kind of areas that we deal with, whether these societal challenges take us to the highest of the mountain peaks. And this is Mount Chomalunga, which is sometimes mistakenly called Mount Everest, by the way, and where I took some of our students from Boston when we visited India and Nepal. Next time when we go, if we happen to go to India, I'd love to visit IIT Gandhinagar, by the way. And the other, picture on the right, that's Goddess Saraswati in Dwijendra University in Bali, Indonesia. And Indonesia is facing one of the, is facing the brunt of sea level rise and flooding and so on and so forth. Some of you may know that their capital, Jakarta, is shifting. And when you think about, Mount Chomalunga, when we think about Himalayas, I don't need to emphasize here to this audience the importance of these on, hydrology and climate systems across the world, but especially in some of the most populated regions of the world, including in India and the Indian subcontinent. So what this shows is the global risk report from the World Economic Forum. The World Economic Forum comes up with risk reports like this every year. This is the latest one. And on the right, on the x-axis here of this graph, you have likelihood of some risk happening. Here's the chance of some risk happening, probability of something happening. On the y-axis, you have the impact, which is if that were to happen, what would be the cost in terms of human lives, cost in terms of economy, et cetera, et cetera. So the more on the top right that you go, that's where some of the greatest risks are from, according to the World Economic Forum. And if we go to this area, what do we see here? We see things like extreme weather, which, by the way, are often intensified by climate change and climate variability, along with other things such as, urbanization, land use change, etc. And we see climate action failure to take climate action. We also see entities that are very much related to climate issues. In addition to extreme weather, we see things like biodiversity loss, natural disasters, water crisis, human-made environmental disasters. So if you look at this part of the spectrum, maybe other than cyber attacks, almost everything is either directly or indirectly related to climate variability or change. And that's going to be one of the focus areas of this talk, how we can use all of this to try and how we can use some of the latest and greatest technologies, if you will, and adopt things that we may have known for a while now to address some of these challenges. Let me first talk about a climate change war game, which I was fortunate to attend. I see some raised hand. All of you can hear me okay, right? Vimal, you can hear me okay, right?
Yes, I can hear you perfectly.
Okay, all right. I was just wondering. So if that happens, please put something on the chat window, in case you cannot hear me, and Vimal will let me know. Okay. Going back to the climate war games. So the first time an international climate war game happened, it was organized by the Center for New American Security. And I happened to be at the Oak Ridge National Lab at that time. And the war game is a role-playing negotiation. So nowadays we hear about Paris Agreement. Paris agreements happen when negotiators from across the world representing their countries get together. And then through various negotiations, they arrive at some agreement. War games try to simulate, try to mock that process. This can happen through simulations, as in computer simulations, think avatars and things like that. Computer simulations obviously have certain limitations and certain strengths, but these can also happen by actually involving the real life human players. And that's what happened here. So what this Center for a New American Security did is they actually got players from US, European Union, India, and China, and then one team which represented the rest of the world. And they tried to mock this process of negotiation. They got people who actually participate in these climate change discussions. The idea was not that you are just looking at the outcome, because outcomes can slightly change as people negotiate, but the idea is to understand how these negotiations work. So that was done in 2008, which was towards the tail end of the George W. Bush administration, to try and understand what can be done when the new administration comes in. Incidentally, they asked Oak Ridge National Lab to help with producing various maps and figures. And that's how I got involved. I happened to lead that small Oak Ridge team. And eventually I was inducted into the War Games team. There were various reports that came out of that, including one by CNAS, Center for New American Security itself. It was called Clout and Climate Change. I'd encourage you to look at that. There's a brief Nature report also on that. This was a news article which highlighted one of our work then. But anyway, the idea here is that when we think about climate change and when we think about acting to do something about climate change, we're broadly talking about two areas. We're talking about adaptation, which has been called managing the unavoidable. And we talk about mitigation, which is avoiding the unmanageable. So the first one says that even if we are to stop, or if we are to control emissions right now, and if we are to control the pace of urbanization, the pace of land use change, deforestation, et cetera, even then, because of things that have already happened, that we have already done, and because of natural variability, certain kinds of extremes, certain kinds of stresses will happen, and we have to adapt to those. We have to manage these things that are just unavoidable. Versus some other things, if we continue with our business as usual, some other things might happen which could be much more difficult to manage. And what we should try and do is avoiding those kind of scenarios. Now, so that is broadly what the big picture that sort of motivated this war game. This picture was created by us. The captions were filled in by Center for New American Security. This is one of the pictures, though. There are a variety of detailed, pictures and such, and science-driven insights which motivated this war game. But that being said, a lot of these discussions are also political and also very much focused on what this means for each individual country. So despite this global need to act, which potentially almost everybody acknowledges at some level, at least the negotiators acknowledge, there are some ground realities. So people talk about resources. What would climate change mean? Climate change or variability mean for food, energy, water, ecosystems, etc. So that's one. Then the other issue is hazards. These are critical infrastructure, lifeline networks, including transportation systems, communication systems, water distribution, electric grid, etc., and other emergency preparedness systems and services. So broadly speaking, hazards and humanitarian aid. So in terms of resources and hazards, what would climate change mean for any country? These things are incredibly important to understand. And for each nation to participate, these often become among the drivers, and these would broadly fall under the realm of adaptation. And then there is population, whether it's population growth, whether it's migration. Migration could be external from one country to another. Migration could be internal, such as urbanization. And things like land use change, urbanization, all of these things which impact or are impacted by population, this falls somewhere in between adaptation and mitigation and becomes very important. In the context of international negotiation, when we think about migration, what becomes also important are this concept of environmental refugees. And then we have all of these leads to discussions around emissions, which include things like fossil fuel, renewables, carbon capture storage, et cetera, and regulations, whether these are at international scales, national scales, et cetera. Right? And there are various elements here. I mean, there are reasons why national priorities often dominate some of these discourse. So a country like India or Bangladesh or some countries in sub-Saharan Africa might say that, okay, overall, if you combine all of the emissions from this country, it can be high, but if you look at per capita emissions, it's not so high. And historically, these countries have not emitted so much. They are now on their development pathways. So is this the best time to stop emissions? Versus the counter argument would be that the idea for these developing nations is not to stop emissions, but to get along a pathway which is, in a sense, better and more sustainable than what some of the currently developed nations have gone through. And the other aspect here also is, when you think about adaptation and when you think about mitigation to some extent, it's important to understand the role of emissions, important to understand the role of urbanizations, land use change, so important to understand the role of climate change and variability, but there are also a variety of other factors which impact these, including, for example, if you're talking about hazards, how prepared are we? If you're talking about resources, such as food, energy, water, how good are our supply chains, how good are our distribution systems, generation systems, etc. So so cases have been made that if there is a need for the world at large to prepare for and reduce the potential impact of climate change and variability, then there's a need for some of the developed nations to take a more active role in helping out developing nations. So these are the kind of discussions that happen. I would encourage you to take a look at this, but what this war games kind of gives us is a bit of context to this entire discussion. When you think of climate science, broadly speaking, very broadly, there are two types of methods, if you will, that are brought to bear. One is models and simulation, and this is sort of captured in the left side, where we deal with all the kinds of processes that we can think of in the Earth system. So these kind of models, these are big computer models. They need some of the largest supercomputers in the world to run. So when I was at Oak Ridge National Lab has some of the world's largest supercomputers. Sometimes they have the world's largest supercomputer, and then there are other countries that sort of get better, and then again Oak Ridge gets better. So it's I mean, those things happen, but Oak Ridge has for sure some of the the grandest high performance computing machines in the world, and all of these are run. I mean, all of these are necessary for these climate models to run. Now, at some point, these used to be called general circulation model, talking about atmospheric models. Then they came to be called global climate models because they dealt with so much more than the atmosphere. And now these are called Earth system models because they deal with so many things besides the atmosphere and ocean and land ice and vegetation, land, hydrology, and so many different things. And including in the atmosphere, it's not just, it's not just solar radiation and things like that. It's also a lot of atmospheric chemistry, it's land atmosphere, ocean land atmosphere interaction. So all of these things are embedded within computer models. And this is the state of the art. If you think of climate change and variability, the state of the art is to look at these large models, simulate Earth system processes, as I was saying, they are now called Earth system models. And then from these simulations, either analyze these simulations, understand these, and get insights about what might happen in terms of climate variability and change, and what the implications are for resources, infrastructures, hazards, population, mitigation, etc. So all of these things you try to look at with these kind of approaches. I mean, with these modeling simulation approaches. There are many processes in climate, weather, etc., hydrology, which we seem to understand fairly well with these kind of models. These are physics inspired, I would say, models. So they have as much physics as we know. We try to embed them within these models. What does that mean? Think of Newton's laws of motion. Think of Navier-Stokes equations in fluid mechanics. But that in the case of atmosphere, it is that same Navier-Stokes equation, but it happens on the surface of the Earth. So that means that you have to treat it in a certain way. The standard things like conservation of energy, conservation of mass, conservation of momentum, all of these things are relevant here as well. So these are physics that we know. However, there are some other things which matter a lot, things such as extremes, whether it's extreme rainfall events which cause floods, whether it's cyclones, whether it's tornadoes, things of that nature. So there are extremes which the physics of which we don't understand as well. And there are components of this Earth system such as cloud physics or hydrology, which again, where we have to rely on what are called parameterization. So these things are not directly, they do not come directly from first principles based physics. They come from physics inspired parameters, but we don't fully know or understand that physics. But we combine all of that, and that's what gives us these big models which takes large supercomputers to run, and this is the state of the art. Now, as I was saying, in the context of many processes, these models and simulations and analysis of data from these simulations seem to work well. However, there has been a growing realization now, lately, that some long-standing challenges continue to remain. So in the atmosphere, this is cloud physics. And there are similar challenges when you think about hydrology, when you think about oceans, when you think about teleconnections, long-range connections that exist in weather and climate systems, such as connection of El Nino with weather systems and hydrologic systems across the world. And the idea is, people have started to think that, well, we have always used statistics and data science with climate in the context of analysis of data from climate models, analysis of observations. But can these new machine learning, artificial intelligence, can these kind of models, can these kind of methods help us, especially to address those challenges which have remained long-standing challenges for a while now, for decades in some cases? So there was this article in the journal Nature. This is a perspective article, meaning more like an opinion article, where they talked about, where machine learning is gradually being used. Now, I have this figure on the left and this figure on the right. They're not at equal levels, if you will, in terms of how much they're used. The figure on the left shows what is being used right now, mainly simulations, models. The figure on the right is an aspiration. Basic data sciences are used in climate. Basic empirical methods are used and have been used actually even before models were used, and they continue to be used now in the context of analysis of observed data and model simulations. However, what you're talking on the right attempts to go a bit beyond, attempts to use some of the latest generation artificial intelligence machine learning methods, and this is very new. So this talks about the things like object classification in machine learning, which maybe can be used to find objects from ensemble of climate models. It talks about super resolution, image classification method, which can be used for certain things like downscaling in climate. Similarly, video and language translation, etc., could be adapted for certain problems in climate. So these 4 examples came from this perspective article in Nature. The second example right here, which talks about super resolution and fusion, is actually one of our work. So this is by Thomas Vandal, who was a former PhD student of mine and is now a scientist at NASA. So he was, he used these deep learning kind of approaches in the context of computer vision and adapted them to this one problem in climate, which is called statistical downscaling. Again, very initial, aspirational at this point. All right, so coming back to climate problems, there are a lot of serious uncertainties. I'll not go into each of these things right now, but one, just to highlight, these uncertainties are not just large, but they are fairly complex, and we understand them. We understand them in the sense that we understand that they exist. We do not understand them always in the sense that we can exactly characterize them, but we try. And there are broadly 3 types of uncertainties. One, because of what is called the forcing. The forcing refers to how the solar rays are modulated. So broadly speaking, if you think of climate system, everything is driven by the sun. Solar radiation comes in as shortwave radiation, and unless there are cloud covers or things like that, they can enter right into the atmosphere. But then the land surface gets heated up, and this heat tries to escape in the form of long wave radiation. And it is this long wave radiation that's trapped by greenhouse gases, such as carbon dioxide and methane. And once this warming process happens, there is a little bit of a feedback effect. So once the atmosphere gets a bit warmer, it can let more water vapor enter into the atmosphere, and that acts as a further greenhouse gas effect. So it's these kind of things, this carbon dioxide, and if there is methane, etc., and also, cloud cover, things like that, which modulate what happens to the sun's rays, which are coming in, so which is called incoming solar radiation, and what happens to the outgoing radiation that's emitted by the Earth after it's heated. So the uncertainty there, that's represented by the green. And that is not too high in the initial stages, but rapidly grows fairly high because of, we don't know how emissions scenarios will look like. We don't know what we'll do as humans, or all the kinds of natural variability that exists. So over time, this uncertainty builds up. The other 2 types of uncertainties, one, the blue one, that's the uncertainty because of gaps in physics. So there are things like I was saying earlier, which we understand relatively well, and there are other things which we don't understand as well, and we have to parameterize. So, and those kind of things are captured within many different model runs. And if we look at all of those model runs, that's what we see as the variability here in blue, that represents our lack of understanding of the physics, which is captured through this uncertainty. And then if you look at orange, this reflects the internal variability of the system. So even if we understood the forcing, let's say the carbon dioxide, water cycle, all of these things perfectly well, and even if we understood the physics perfectly well, there is an intrinsic variability of the system which would remain. Now, this thing that you're seeing here is at global scale. The intrinsic variability increases. The share of intrinsic variability, which is in orange, increases when you get to higher and higher resolutions in space and time. And especially in the critical near term in climate. In climate, near term is defined as 10, 20, 30 years. That is very important for decision making, and that's where this kind of uncertainty dominates, internal variability kind of uncertainty. Now, uncertainty in this case does not mean that we cannot act. Uncertainty is not an excuse for inaction. In many cases, almost all science engineering problems, we have uncertainty. When we design a bridge, we have uncertainty. We don't know the traffic exactly, right? If you are building a bridge over 50 years, its lifespan is 50 years. You don't know, or you don't even need to know the traffic in each in each minute, each hour, each day in all those 50 years. And we know that there will be uncertainty, but the idea will be to build that bridge together with its safety factor in a way so that it can withstand despite the uncertainty. And that's the kind of thing we try to do here, that we try to understand the uncertainty. We understand first that these uncertainties exist. We try to understand the uncertainty. We also understand that there is a trend here. There is some physics that's driving a longer term trend. And collectively, we sort of try to translate that into risk analysis, design principles, etc. So I'll try to intersperse some of my talk with some pictures and figures, lest it gets too boring. And from our group, we go to each year, I take some undergraduate students, go to different parts of the world to study climate variability and change. On the left is a figure of Machu Picchu in Peru, which was a variety of things. One of the functions of this, as we understand now, is that it used to be a scientific observatory. On the right are two of my current PhD students, Kate and Nishant, and they are working in physics-guided deep learning for a variety of things from weather and climate and ecology, etc. Kate is an intern at NASA. Nishant will become an intern soon, and Kate will, once she finishes, she will join NASA like one of my former students. Okay. I was talking about translating some of these uncertainties and trends and variability to risk. When we think about risk, we think about several things. We think about the driver. So climate change is an important driver. It's not the only one, but it is an important driver. And when we think about climate change, we have to realize that we are talking about global warming. So overall, we are talking about warming with variability. Not all years will continue to be equally warm. There can be a lot of variability within that, but there is a big overall trend. Despite that trend, despite that overall warming, which is here the shift in the mean, how the extremes will behave is not always as clear. So just because globally we are having warming doesn't mean that we'll only have heat waves and all cold extremes will vanish. It could be that we'll have both more extreme heat waves and more extreme cold waves, as well as overall shift in the mean. So it could be all kinds of things that could happen. And that's some of the things we have to understand when we look at drivers. So besides climate change, which includes natural variability about which we may not be able to do much, and human-induced climate change about which by controlling emissions, land use change, etc., we may be able to, we meaning collectively as humanity, we may be able to influence this. But overall, these things leads to hazards such as weather extremes. But none of the weather extremes by themselves are enough to lead to disaster risk or impacts. These weather extremes or these hazards interact with vulnerability, such as vulnerability of infrastructures, levees, dams, reservoirs, and with exposure, such as society, people who are exposed, assets which are exposed. And then collectively, the hazard, vulnerability, and exposure collectively leads to losses, expected losses or threats or risk. And some of this risk can be addressed by developing better ways for adaptation and mitigation, developing better social and economic pathways and policy tools. And one other thing to remember also is that it's not just the total amount of risk that we are worried about often, but we also care about recovery. Once something happens, can we recover fast enough, and can we maybe even learn lessons from this failure and get to a better state? And that's sometimes called anti-fragility. And the other thing is, even though we know that even despite some of our best efforts, bad things will happen, hazards will happen, but when they happen, instead of losing functionality completely or significantly, can we at least design our systems, operate our systems so that we retain at least basic functionality, which will let us continue with our lives, even if in reduced forms? And we think of resilience in the context of, for example, weather-related hazards, hydrology-related hazards. And we think of them in the context of cities and villages. For cities, we often think of interconnected systems, whether it's water, transportation, power distribution, financial sector, energy sector, communications, etc. So the first talks about characterizing risk in the context of hazards, vulnerability, exposure, and what can be done about it. The second goes one step further and says, okay, systems will degrade, but can we understand the system well enough to design in advance efficient recovery strategies, maybe even get to a better state than where we were by learning lessons from the hazards? And can we design and operate our systems in a way so that we don't lose functionality completely, right? And that can be in the context of, for example, weather extremes, in the context of what are called urban lifelines. I talked about urban lifelines. Now in cities, that's where most of the economic activity around the world is happening right now. In developed economies, it's very much focused on cities. As economies are developing, we are seeing increasing urbanization, but it is happening everywhere. Now, if you map some of the world's top cities in terms of expected GDP in 2035, look, we have New York, Tokyo, LA, London, and then we have Shanghai, Beijing, etc., and then Paris, etc. So it's dominated by Western cities, European and United States, and then of course, traditional developed economies, Japan, but China has been rapidly coming in here. If you look at the world's top cities in terms of 2035 expected population though, it's a different story. It's Jakarta in Indonesia, at least now. Indonesia may shift its capital from Jakarta, and then that may cause a little bit of change here, but it's there. Only some developed nations like, Japan, etc., they have their big cities here with that large population density, but in general, it's all dominated by Bangladesh, Pakistan, and there's only one entry from India, which is Mumbai, which is at the very end. But so it's very different when you look at these cities by GDP and by population. And it's important to address both kind of challenges. And then if you think of rural areas, we think about agriculture, and look, if you look on the right, this is a map of value added per worker in agricultural sector, and this is a map of total number of workers, the share of labor force in agriculture. So if you look at, for example, just compare US and India, the share of agriculture in India is much higher, as you might expect, compared to the US, but the productivity per worker in the US is much more than it is in India. And this is common across the world in terms of developed versus developing economies. And of course, India is a fairly special case because it's both an underdeveloped economy still, it's developing, but it is an emerging economy. It produces, after some countries such as US, it produces one of the largest number of billionaires these days. But it also has among the world's largest population of malnourished children and people who are economically not at all well off. So the conditions of a lot of people in India are actually worse than sub-Saharan Africa, which you think as among the least developed. So India has both of these. So it's a very, in that sense, it has some unique challenges, as we all know. But here I wanted to highlight also is that there are various agricultural technology these days which are coming up, which may be able to address some of these issues. Some may be useful, some not so useful, but there is no dearth of technologies in these areas now. In the context of water, if we look at water resources, providing drinking water, if we look at water-related extremes, so droughts and floods, if we look at nexus of water with food, energy, ecosystems. And if we look at water infrastructures, these are things that are impacted by all of these drivers that I was just mentioning: climate variability change, land use, population. And these seem to be impacting us continuously across the world, both in developing nations as well as in developed nations. And one thing that comes across sometimes, to me at least, when, for example, when I think of water infrastructures, is I'm not sure if as a civilization over millennia, over hundreds of years, thousands of years, if as a civilization we are improving in terms of providing service levels with water infrastructures to our population. Perhaps if you think of Harappa and Mohenjo-daro and places like Rakhigarhi and elsewhere, where we used to have what is called the Indus Valley civilization, but now we know it spans a lot more than just the Indus Valley area-wise. If you think of water and sanitation infrastructures in those parts of the world at some point, thousands of years back, I'm not sure if in terms of service levels, those same areas have gone up or gone down. So if you think of water as a service for communities right now in those areas, whether it's in Pakistan or even in Northwest India, has it really gone up? I'm just talking about service levels. Of course, over thousands of years, we have had technologies. But in terms of service level, has it gone up or gone down? That's an interesting question. And are we learning the right lessons from history? All right, so now going to artificial intelligence, as talking about artificial intelligence, as talking about, some of these things are being touted as among those novel tools, methods, which can really create major, trust and really lead to new developments in this area, help solve some of our problems. Sometimes artificial intelligence is sort of touted as everything. So all these problems that we'll have, artificial intelligence will solve, right? Everything. And then sometimes we hear about, oh, these are the most dangerous things that are happening. It's important to look at these. And there is no doubt that artificial intelligence is helping us tackle many different problems in many different ways, right? So what is the issue there? So this is a sort of a plot by the Gartner Group. Gartner is a group that thinks about business trends and is very much valued as a consulting company. And they come up with these things called hype cycle. So they say that every technology, when it emerges, has an innovation trigger. And then initially people think that it will solve everything. So there's this peak of inflated expectations. Then people realize that, oh, it'll not do what I thought it'll do. So there's this trough of disillusionment. And then over time, people understand, okay, these are the things that it will do. These are the things it will not do. So that's when you get to slope of enlightenment and you actually start to solve problems. And if you think of these innovations and peak of inflated expectations in 2020, pretty much everything or a lot of these things seems to be one way or the other connected with artificial intelligence or machine learning. Look at this, explainable AI. Maybe social distancing could involve AI, but it's not just AI. So, and this, because we are living in this era of the pandemic, it's right at the top. But if you think here explainable AI, if you think here embedded AI, data fabric, AI augmented development, responsible AI, so generative AI, adaptive machine learning, adversarial networks, brain-machine interface. So it's the entire chart here is dominated by artificial intelligence. Now, when we think about problems, whether it's climate, whether it's infrastructures, whether it's agriculture, water, etc., more and more we are realizing that data-driven sciences, machine learning, artificial intelligence, by itself, by themselves, may not be enough. There is no reason for us to discard all the theory, and which may be in the form of physics, biology, chemistry, biogeochemistry, or economic theory, social science theory, all of these things that we know, and we have collected this wisdom over the ages. There's no need for us to discard all of that. At the same time, there is a need for us to take advantage of these embedded systems, which include AI-driven systems, as well as the big data revolution and new data, whether it's big, sometimes it's small, but it's still new data that we are getting. All of these things is important to connect all of these to the theory. So what we are evolving towards over time is trying to integrate scientific and theory, engineering principles, policy imperatives with data-driven sciences, with machine learning, with AI. Long time back in 1989, the eminent physicist Roger Penrose, whose work I'd encourage all of you to read, wrote this book about which he called The Emperor's New Mind, concerning computers' minds and laws of physics. And he said that, you know, whatever we think about AI, machine learning, computational methods, they'll solve all kinds of problems, but there will always be some difference between artificial intelligence and natural intelligence, and laws of physics will never get completely outdated in this. And we are realizing the wisdom of that. This book was written in 1989. We are realizing the wisdom of that more and more. So what we are talking about these days is trying to blend, trying to integrate many of these approaches. So that was a statement of the problem. Now I'll go through a bit quickly with the rest of the things here. I'll be happy to discuss eventually. I'll talk about solutions which can apply globally. Some of the pictures here again, by the way, one is Alaska on the left. In the middle, that is the river Amazon in Brazil, and that is a boto, that is a pink dolphin, pink river dolphin in the Amazon. These are, some of them are my students whom you see here. And on the right, that's a fjord, that's in Norway, it's a Norwegian fjord, right? So many of these things that we'll study apply to all of these natural systems, and these systems in turn contribute to some of the things we're talking about here. So in terms of data, right? So we talked about bringing data physics together. And sometimes we talk about big data, and definitely we need to get insights from big data. But not all problems in science and engineering can be called big data problems, right? So we may have a lot of remotely sensed data right now, but if you go back in history, we still have small data. To be able to get insights from data, whether these are big or small, is important. And here is an example with what is called teleconnections. These are long distance relationships between weather and climate variables, right? Such as some of you may have heard about the El Nino. So here I'm showing the use of nonlinear physics, nonlinear dynamical methods such as mutual information and things like complex networks applied to spatio-temporal data set to extract various kinds of insights. We can talk about data sciences or statistics that are applied to model simulations, and you can sometimes get interesting and insights, such as here we got some insights about heat waves, which were somewhat expected, but there were some interesting twists about this. And then we also got an insight about cold snaps. So we saw that heat waves will intensify, but cold snaps, even in a warming environment, might persist with certain specific definitions of persistence. And this was an interesting insight. It got highlighted in Nature because of that. And this other one about heat waves talked about geographic variability and uncertainty. And later we are able to work on both of these, both extremes, and find out a bit more through extreme value theory kind of analysis. So this analysis of observations and model simulations, right? The first one I showed is analysis of observations. Second one I showed is analysis of model simulations. Both of those kind of analysis, you can make this analysis much more focused and targeted. For example, if we are trying to understand extreme values, we often look at what is called extreme value theory, and we have applied that to precipitation extremes across the world from models and observations, precipitation extremes in India just from observations, and then heat waves and cold snaps across the world from both models and observations, right? So you go from empirical methods on big data, small data, to data sciences applied to simulations, to more focused, or maybe we could call them more sophisticated data sciences, which target certain attributes such as extremes. And then you can go to deep learning, machine learning. And here we show one example of deep learning. I was talking about my former PhD student, Thomas Vandal, and here is our photo at NASA Ames. And this is your Professor Udit Bhatia, who is at IIT Gandhinagar now. And you know, the whole idea here was, I mean, if you, for now ignoring the methods and such, the whole idea was that you can treat statistical downscaling in climate as a computer vision problem. So once you adopt methods in computer vision, you can address this problem. At the same time, it's not enough to just adopt, you have to then adapt. So first you say that these are methods I can bring in, but then you realize the methods as they are will not by themselves address this problem, and then you need to innovate on those methods. So that is what is called deep SD, deep learning based statistical downscaling. It got an award in a computer science machine learning venue. These kind of venues are very hard to get into, so it was a big deal for TJ here, Thomas J. Vandal, to get this award. But then you have to adapt this significantly. So for example, many of these methods for uncertainty were based on relatively simplified assumptions, such as, you know, you have normal distributions, et cetera, et cetera. Of course, those kind of things will not work. So you have to take those methods, adopt them, but then take them into and say, okay, how can I adapt them to my kind of problem? And that itself might lead to new kinds of innovations, right? Such as here in the context of Bayesian deep learning for uncertainty estimates. And then there are other problems that remain, such as what happens in non-stationary climate. And finally, we get to physics guided. So here is an example of physics guided uncertainty quantification. And you can look at this paper, which has just been published in Scientific Reports, where, you know, Evan Kodra, one of my former PhD student, Udit Bhatia, about whom I spoke, they're all authors. And this talks about, you know, looking at climate models, simulations, and coming up with uncertainty assessments that look at data, look at Bayesian methods, look at some of the best statistical methods that we have, but combine that with our physics understanding. Talking about physics understanding, one other thing that we are trying to do is develop methods based on machine learning and you know, different types of machine learning, whether it's deep learning, whether it's Gaussian processes, to address some core challenges in climate and weather systems, such as cloud systems, cloud physics, or hydrology. And trying to look at this first step of what kind of methods can be useful. So this is with my current student, Nishant Yadav, and a collaborator at MIT, Sai or Srinivas Ravella. And this also got a best student paper at one of the workshops. So when we think about climate, by the way, I mean, again, you know, it's a problem that's global. Here I'm showing a glacier in Alaska. And just so you get an idea, if you look at this small bump here, right, that would be the size of large ships. So in this figure, in this photo, I don't have a ship here, but there are some photos with ships. It's the size of this very small thing right here. So that's the size of some of these major glaciers, and many of them in the poles are melting very fast, right? And all those kinds of, you know, sea ice melting, global warming has been called a polar phenomena, mainly because a lot of the effects happen in the poles, but these things impact things all over the world, including, this is when we visited Indonesia. So this is the Indian Ocean in Indonesia. These things are incredibly interconnected, right? So so in the world of climate, it's very hard to draw boundaries and put visas, because phenomena like El Nino, which is a climate weather phenomena, will not respect any of these political boundaries. All right, so going from there, going from embedding machine learning to understanding the physics, or using machine learning to understand the physics, or just broadly using data science statistics, we can also go the other way and say that can we extract process insights from physics? So I was talking about how the world is interconnected in the context of Indian monsoon. We actually found some of those things. So in the last cycle of what are called these IPCC, these United Nations models, we found that certain characteristics of Indian monsoon actually are best captured in the Norwegian model. And when that sort of made us think, why is the Norwegian model, what do they have? Why are they capturing certain attributes of Indian monsoon, right? And then we realized that attribute of the Indian monsoon, which is a 60 to 65-year cycle, corresponds to an Atlantic multi-decadal oscillation, which also has a 65 to 70-year cycle because of a series of physical explanations. And it's that thing which is close to Scandinavia anyway, which this Norwegian model was capturing. So to understand process physics at global scales, right, we can also use these data-driven methods. And beyond all of these, beyond understanding the physics from empirical observations, from model simulations, and then looking at machine learning to help in these models, looking at machine learning to extract processes, looking at combination of machine learning and physics to improve uncertainty, improve insights, and using machine learning to get some insights in the first place, all of these things, then needs to have some value. There has to be something why we are doing this, some reason for that. And that reason is the impacts, consequences of climate change to which we need to adapt. This is one of our publications. This one was in Nature about how climate change has implications for coastal upwelling, which is an important process when we think about coastal and marine ecosystems across the world. And we saw that biodiversity loss is one of the major challenges facing humanity and facing our planet right now. And this again is across the world. I have some photos here from our visits across in Indonesia and Amazon. This, by the way, is the fish piranha. Many of you may have heard about that. And this is a baby caiman. It's not, caiman is the kind of crocodile that's found in the Amazon forest. And this is a floating forest, it's called. Right, and these characters, I think all of you recognize. So all over the world, this climate change variability impacts key processes such as coastal upwelling, as well as biodiversity loss, and has implications for agriculture. So here is one of our recent papers in remote sensing of environment, which looks at crop yield projections and how we can improve that with data-driven methods, which are guided by ecological considerations. So theory-driven data science, in this case, ecology-driven data science. And what weather and climate change could mean in the context of crop yield. In addition to ecology and going from ecology to crops, we have looked at the water energy nexus. So in terms of, if you think about power production at risk, what happens both because of changes in water availability and because of rising stream temperatures. And if we get to a situation where we have warmer water temperatures and less water, that's when power production may be at risk. And remember, when you think about power, it's not just hydropower. Almost all power plants use significant amount of water, most of it for cooling. And one of the major things that is important in this context is, what about our infrastructures? What about our lifelines? And by lifelines, I mean things like, as I was saying earlier, transportation network, electric grid or power grid, communication network, water distribution, wastewater systems. And here are some examples with different kinds of transportation systems, and in one or two cases, a combination of transportation with power grid. A lot of this work recently has been done by your Professor Udit Bhatia when he was in my lab, and then recently we have been doing some others. So here is some work in India, in Indian Railways, London Rail. This is different types of urban railways. This is the US airport network. This is the city of Boston Rail network. This is Boston Rail Network together with a simulated power grid, etc. And all of this then needs to be translated to what can be done for cities. So our group, our lab has been working very closely with the city of Boston to help them with Climate Ready Boston report. Then with the town of Brookline, which is a suburb of Boston, to try and understand public health risk in the context of urban heat waves. I'll not go through the details right now. And then also to think, and this is an article that you might want to check. This was in the United Nations Association of the UK. This is called Climate 2020. It has our article, but there's also some other interesting articles where, in addition to thinking about climate risk and resilience or recovery, we are also thinking of the incentivizing resilience. So how to translate this vicious cycle of financial disincentives, economic stagnation through startups, through transformative science into a state where we can be more ready for the change that we expect. And some of our own work has involved, in addition to the sciences and publishing papers, and hopefully, adding incrementally to our total state of knowledge, also helping through technology transfer, coming up with patents. This is my former PhD student, Evan Kodra. He has a patent for climate change forecasting and uncertainty, which partially led to this company, which was originally founded by NSF and now is embedded in the Intercontinental Exchange, which is an exchange for financial risk in the context of municipal bonds. And this company is called RISQ, Risk, Quantifying Risk. And it looks at financial risk under climate change. So that was one kind of, one area of technology transfer. This is a startup company based in Boston, where my former PhD student, Evan Kodra, is the CEO. And then there is this other patent about resilience, which talks about both destruction and recovery of network systems. And this was led by your Professor Udit Bhatia. So with all of these things, there are several opportunities for sustainability with a focus on India. By the way, this on the left that's me on a small plane around the Annapurna range, and that's in Sikkim. So anyway, so in India, there are some opportunities and there are challenges with what we call theory-guided AI, or what I'm sort of this integration of scientific theory, engineering principles, policy imperatives with artificial intelligence. I'll not go through all of these things in too much detail now, but one area where we think we can improve is deep into these Earth system models itself. And this could include, so if we call this water in the atmospheric system, there are some key gaps, such as from oceans, the oceanic climate oscillators, as they are called, influence atmospheric processes and regional climate. These are sometimes called teleconnections, things like El Nino, and our understanding there from models, simulations is not as good as we want. Things like just the hydrology itself, whether it's groundwater, whether it's surface water, whether it's land atmosphere interaction, again, a lot of gaps in that understanding. Within atmospheric processes, things like cloud physics, whether these are at mesoscales, whether these are at decadal scales, not very good. So many of these things we can start to improve in the context of the Earth system models that exist today, but by bringing in some of these artificial intelligence methods. And a few of the approaches that I showed you earlier, where we are using machine learning for certain kinds of models, which are idealizations of cloud physics models, or whether we are trying to discover process insights, go sort of in that direction. And then when you think about uncertainty assessments, they include those, but they also include assessments of simulations from these models. So we have been working with a variety of partners in these areas. And then in terms of impacts, of course, I don't need to tell you this about the challenge of agriculture. So in India, we often, and across the world these days, we are seeing this drought deluge cycle. In different years, or sometimes in the same year in different regions, we have major droughts and major floods. This is one of my acquaintances. He's Dr. Sheshagiri Rao. He calls himself a PhD farmer. And somewhere in Tamil Nadu, not too far from Bengaluru, he has his own farm where he uses technologies, like he says, all the way from old technologies from ancient India and ancient Mayan civilization, all the way to latest decision sciences, AI kind of technologies and water technologies. And some of it may come across as science fiction, but it's fascinating when you go to his farm. The entire place, when we were going there, is brown and dried leaves, so it's going through a drought. But when you go to his farm, it's all green. So there are things that people are doing. It's not just all AI, it's not just all water science, it's not just engineering, it's a combination of all of these things. Similarly, when we think about how interconnected systems are in India, so this is, monsoons and heat waves because of agricultural water policies lead to abstraction of groundwater and also lead to stresses on the power grid, which can cause massive blackouts, which can cause, because through signals and systems, impacts on railway networks. So these interconnected systems of natural, human, policy, and infrastructure, and the potential for cascading failure is something that needs to be looked at. In addition to failure, some things like the interconnection of refuse burning, crop burning with urban air pollution, and how that relates to groundwater policies. I mean, I don't need to say this to you. All of you are aware of this at some level. But these are very interconnected themes. And to be able to solve them, you cannot just look at groundwater, cannot just look at urban air pollution, cannot just look at crop burning, bioenergy. You need to look at all of these things together at the interface of urban, rural, science, policy, environment. So all of these grand challenges, can we just say that artificial intelligence is the solution and that's it? Well, I already said that, we are finding that it's not just that one thing. I mean, that may offer some solutions, but it has to be looked at in the context of the theory that exists. And that theory, again, can come from scientific insights, physics, chemistry, biogeochemistry, biology, bio-inspired, nature-based design, all of these things, plus engineering principles and policy imperatives. Just as an example, so here we have a timeline of how artificial intelligence evolved. I'll not go through all of these, but suffice it to say that artificial intelligence has gone through various waves. At some point, it was highlighted as, oh, it models the human brain, it's going to solve everything. And then it went through some deep winter, as it's called, AI winter. Nobody thought about this. And suddenly it comes back and it goes down. Right now, because of deep learning and how much it has been useful, it has found to be useful, it has again gotten all our attention. So here is Andrew Ng, who is an expert in deep learning, machine learning, and he has said AI is the new electricity. Here is my batchmate Sundar Pichai, who I mean, all of you know, I guess, and he says AI is the most important thing, more profound than electricity or fire. Even physicists have been sort of cautioning us about AI. Now, the people who really deal with AI and are really involved in making who have been really instrumental in driving some of the serious AI innovations are a bit cautious. So here is Professor Michael I. Jordan, currently at Berkeley. He used to be at MIT earlier. So he says that AI revolution hasn't happened yet. And he compares that incidentally with the initial stages of civil engineering. So just as civil engineering, he says, is built on physics, chemistry, and so on, this new engineering discipline will be based on things like information, algorithm, data, uncertainty. And he says there was a time in civil engineering when we may have said, oh, this bridge, it's too dangerous. Engineers designed it. I don't know what will happen. Or should I enter this building or not? My life's at risk. We don't think about civil engineering anymore in that sense. So we have matured as a field. And his comment was that artificial intelligence is yet to get to that stage. This is not to say that artificial intelligence is not already doing a whole lot. It is, and we should use its potential. We just have to be cautious, and we just cannot discard all the other things that are out there, such as all the science and engineering and policy. Couple of things to remember when you think of artificial intelligence. Each time we see this new incarnation of artificial intelligence, certain things come back and forth. There is this Occam's razor, which says models should be as simple as they can be given the data. And AI systems, deep learning systems, for example, definitely are not that simple, at least on the face of it. So there is that balance that always comes back. People often talk about the brain, something that's a neural connection, and you think, oh, is it the brain? And well, there are all kinds of things. Then there is this recent paper which again says that, okay, we solve all these things with artificial intelligence, but we don't really know why. And these are top venues, top journals. That doesn't take away from what artificial intelligence can do. And deep learning, these pioneers of deep learning, for example, won the Turing Award, and they have found a lot of use. People have sort of built on that to build uncertainties within these deep learning approaches. But the climate problem, which includes what is called chaos theory, which includes these very deep physics, biology, biogeochemical challenges, these engineering challenges when you think about infrastructures, agriculture, when you think about impacts of climate change, these various statistical, deterministic, and kinds of uncertainties and critical challenges, these require a bit more potentially. So we need to continue to work in these areas. And one thing that people have said, so this goes back to that Nature article again, where they sort of cited one of our work as among the 4 recent works in machine learning and physics. So we need to go back at that, machine learning and physics. And some of us have been trying to say that for a while now. So, there is this, some people have been calling it theory-guided machine learning. I mean, Professor Vimal Mishra and I, we were involved in some work way back now in nonlinear processes and geophysics, where we tried to sort of put this viewpoint together, physics-guided data mining. I have been working with some of my collaborators at University of Minnesota, where they have been saying this. And these days, increasingly, people are realizing the value of that. So we have physics-guided neural networks, physics-guided this, physics-guided that, and variety of ways to combine physics and data science, whether using data science to enhance physics, understand physics better, or using physics to inform data science. There is no doubt, by the way, that when we think about broadly artificial intelligence, when we think about data science, Internet of Things, embedded systems, network science, game theory, optimization, all of these collectively, we are looking at potentially a serious revolution. At the same time, we have to be pragmatic, we have to be understanding of the deep challenges and balance with all the things that we know, all the physics, all the biology, chemistry, engineering, policy that we know, and bring these things together. Professors don't do anything without their students, postdocs, and visiting professors. So I'll not be able to name all of them, but here are some of them. I should start listing some of my undergraduate students here as well, because they are making serious contributions. And all I say to end is onward. Let's move ahead. A lot of things to do here. Vimal, that's it from me for now.
All right. So thank you very much for this very interesting, enlightening talk, as always.